So there's an online textbook. Show you what it looks like. It doesn't look like a regular textbook. You know, it's not divided up into pages and stuff like that. But it's a Python reference. And it's a good idea to have a Python reference because our book is not geared specifically towards Python. While this one's all about that Python. It's called How to Think Like a Computer Scientist. I guess that's a Python. Kind of makes sense. So, if we take a look at it, if I asked you a question about how to define a function, you can zip to this website. You click on functions, and then boom, we see a definition right there. All right, but I'd probably ask you for a real example. I wouldn't ask you for an example of a turtle. I don't know why their first example would be done with a turtle. Alrighty, so maybe this is not going to be the best example, but you'll at least see the syntax for it. Yeah, why is it all about turtles? Eventually you can scroll down and see writing a function. And what do you know? This is actually the interest function. It implements that interest calculation, right? And returns it. And what do we see here? We see that it accepts parameter variables and it returns a value. So that's useful to know, right? That's a useful thing to know. So let's go back to the beginning, and we're not going to step through this, you know, as though it were a PowerPoint, because that would take up all the class and more. But the way of the program. The Python programming language. Python is known as a high-level language. There are plenty of other high-level languages. Just a sec. I need a way to zoom the text only, so I'm going to switch my Google accounts. Because I have an extension that'll zoom text only over here. Alright. So this thing, when you pop open idle, you're thrown into what's known as the Python shell. He calls it the Python interpreter. Either term's good. When you see the 3 arrows, that's called the Python prompt. We don't do much in the Python interpreter. We don't type much into the Python prompt. Instead, we want to write programs.
Are you in, which of the tabs are you in?
I went into the one called Way of the Program. Chapter 1.
No, I'm saying, is it under books, tutorials, courses, projects, Python?
I just linked it right now in news. I can also put it in books. Let's see if...
No, I'm saying I'm in open book project now, and I was just wondering which one of the tabs did you go under to...
Is this what you see?
No.
Okay, then go back to our news and follow the top link.
Say go to news.
Right, our front page. Our front page. Right. Sorry, I called it news, but instead of... It's on our front page of D2L, How to Think Like a Computer Scientist.
Okay.
And we went into Chapter 1. So the first one is showing that you can enter commands directly in to the shell, which we almost never do. Instead, we put them in a program because you'd want to do them over and over. You'd want to be able to edit your program, run it repeatedly. And if you're entering commands into the shell, you can't do all that. It just kind of is a one-shot thing. It's like picking up a box yourself rather than giving somebody else a list of instructions on how to pick up the box. So yeah, I could type A is equal to don't do this. Print A, and great, I've done it. But what if I want to do it again? What if I want to do it over and over? Well, it's just in the shell. I don't know why he calls it in the interpreter when it says shell up there. I'm always going to call it the shell. What is a program? Quite often, our programs involve this. Input, get data from the keyboard. Where's the chipmunk? What's making all that sound? Oh, it's a chair wobbling. Okay. And then output. We know how to get input, but we're going to talk about it a little bit more. We know how to display output. It's a print statement. And then doing math, right? And then doing conditional things, if statements, and doing repetition, performing some action repeatedly, usually with some variation. Alrighty. Is somebody wiggling a chair? It's really getting to me. I apologize. Alright, so what is debugging? Debugging is a complex process. It's writing the code and then finding the errors in it. The first thing you got to do is you got to fix all the syntax errors. Once you're done with the syntax errors, then you can actually begin debugging, which is making sure that it works, right? If it crashes in the middle, obviously it's not working. But if it doesn't crash, it may not be correct. If your program is supposed to take one number and raise it to the power of the next, but it only prints the original number, then that's a problem. And you'd have to go and open your code and look at it carefully, you know, maybe add some extra print statements to figure out where it's going wrong, stuff like that. Where did the term debugging come from? It goes back a long way, but it predates programming in computers. But the people who were working on the computers in the 40s and the 50s, a woman named Grace Hopper was keeping detailed notes, and this is the first actual case of a bug. They found a moth that was stuck in the relays of the computer. So they called it a bug. But obviously the term actually, you know, predated that. Bug is just a time when the program does not work correctly. There are several different kinds of errors. Now, I believe our book called them something different than this, so I'm not going to harp on these things. Instead, I'd rather find what the book calls them. Syntax errors. We know what syntax errors are. But let's go and hit this and take a look at chapter 1. And if I was taking an exam and I knew that PowerPoints were open, then I'd probably open all 3 PowerPoints first. And then I'd hit Control F or Command F, and I might hit error. Alrighty, so here we see something. What is syntax? Those are the rules governing word usage and punctuation. See how fast I found that if I asked you what syntax was. I'm telling you how to cheat, right? Since you have the PowerPoints, you can use them. You know, just open it up, hit Control F or Command F, type in a keyword and see what you find. And then mistakes in a language usage are known as syntax errors. So that's one of the 3 kinds of errors. Let's hope that the textbook says 3 types of errors. And we can put these directly in idle. What lecture are we on?
After K.
Alrighty. K was our last one, or is that what?
L, we're on L.
Okay, we're on L. Okay, so lecture L, Jeff, March 12, I believe. Alrighty, so syntax errors, mistakes in the grammar. Of the program, like we don't follow the rules of the language. I'll give you an example of a syntax error. Print equals, you know, enter X. You can't use the equal sign. It may not even call it a syntax error. That one might just blindly run and then erase the print function from your code. You leave off the closing parentheses. Right, that's a syntax error. There's 2 problems wrong with this statement. 2 things wrong. One is you don't use an equal sign. You only use equal sign on the input statement, not the print. And then 2, there's a missing parentheses. So 2 things wrong with that. That's a syntax error. Now let's get the textbook definition out of the PowerPoint. mistakes in a language usage. All right, I called it the grammar. Textbook says mistakes in the language usage, right? All right, I'm going to take a peek back over here and find another mistake, another error, type of error. So I'm going to hit Control F and type in error again. Here we go. There's another error. Here we go. Another kind of error. A logical error. An error in a program logic that produces incorrect output. We type in that the patient has a temperature of 107 degrees and it doesn't warn us that they have a fever, even though it was supposed to. So there's logical errors. The program compiles but doesn't do what it's supposed to do, right? There's no syntax errors. But program does not do what we want. Right? Does not produce good output. And my example, temperature of 107 should say fever, but it doesn't, so we forget to prescribe aspirin. 107 is bad news. There better be more than aspirin involved there. Now that how to think like a computer scientist called this a semantic error. I don't know why he felt the need to come up with that fancy of a term. I'm not saying he because I assume that every computer scientist is male. I just happen to have seen the name of this particular author. All right, I'm going to continue to hit Control F and see if I find a third kind of error. Syntax, logical. There's a third kind that I wish they had mentioned called runtime errors. I'm going to go ahead and add that. A runtime error is when the program reaches a state and crashes. Or maybe I'll just say when the program crashes. Like you try to divide by 0. Computers won't allow us to divide by 0. All right, I'm going to number these. Syntax error was 1. Logical errors was 2. And then runtime errors was my own addition, so I'm going to put it in parentheses. Syntax errors are the easiest ones to find because the compiler tells you. As soon as you run it, you get a red message saying, hey, didn't work, right? You messed up your print statement. You messed up your input statement. That kind of thing. So planning the logic. You have two tools for planning the logic, drawing flowcharts and doing pseudocode. Now, pseudocode is not a programming code. It's not what you enter into idle and actually have it work, right? That's a programming language. Python is a computer code. Pseudocode is a representation of it, a loosey-goosey representation of it. So we're allowed to say input X. Input X doesn't work in Python. It has to follow a very specific syntax or it's a syntax error. Pseudocode can be turned into any programming language. I could take one of the pseudocodes that we do in this class and give it to a C++ or a Java programmer, and they'd be good to go. The language would be completely different. The input statement for C++ looks dramatically different than it does in this language. Doesn't mean it's harder, it just means it's something new you'd have to learn if you're learning that language. Desk checking is when you go through a program's logic on paper. I think I did an example of that. Like if you have a program, and so you write X and Y, and you run it, right, and then Y changes value because they typed in a 2, and then the next line they typed in a 4 there, and then there was a line that said, X equals X times Y, and you'd have to figure it out, okay, 2 and 4, okay, X became A, and that kind of thing. That's called desk checking. Quite often you'd make an Excel spreadsheet to do that, and you're just checking it by hand as though you were a computer, and you really only do that when you're stuck. You cannot figure out the logic error. So syntax, misuse of the language's grammar rules. The programmer will correct every syntax error, or else the program won't even start to run. You might need to recompile the code several times, right? So when you ask me for help and it's been too long since I, walked around, sometimes we have like 4 or 5 different ones to fix. That's why I should be asking more often so that we can catch it early. That's why when I'm writing, I try to, about every 10 lines of code, I ought to save it and run it, even if the program's not going to do anything, just to make sure I haven't put any syntax errors. The earlier you catch them, the better. So testing is executing the program with sample data. It's supposed to tell you when you're allowed to vote. You have to be a citizen and your age has to be 18. I run it and I find out it crashes if I type in the age of 17. Then I have to debug it. I have to figure out why it crashed. I want to make sure it produces the correct output, so you test it to see if it produces the correct output, but then you go one step further and see if you can make it fail. And that's the thing that most programmers don't like to do. They write the program and they want it to work, right? But if you're going to give it to some user, the user is going to find a way to crash your program, so you better find it and correct it first. So maintenance is when you're fixing a program, right? I've written the world's best program, and I give it to Lindy, and eventually she decides that she wishes that all the input was done in French. Shame on you. I would take the program back, and I would make all the changes necessary to make it ask questions in French. It's called maintenance. Or somebody decides that they need an extra report, right? They need a cost analysis program. So somebody would get that program, and they would add a new function to generate that report. That's called maintenance. It's a common first programming job. And you get into a complicated program, written by a programming company. You're the new guy on the block. You're the new girl on the block. And then, people give you lists of changes you need to make or bugs that you need to fix. And that's how you learn the product. That's how you learn what you're supposed to be doing there. So pseudocode, it's just the English. Input X. Print Y. Set Z equal to X plus Y. Right? Doesn't follow syntax, doesn't have colons, doesn't need parentheses. Now, if I ask you for pseudocode and you're putting colons and parentheses and stuff like that, you're trying way too hard. I'm not going to count off because you put parentheses in it, but you're trying way too hard. And in a flowchart, it's just a picture of the pseudocode. You take the pseudocode and you turn it into a drawing. Pseudocode looks like this. Always begins with start, and then everything after the start is indented until you hit the stop. You don't need to put a start and a stop command if it's Python code, right? We could put that in a comment, but there is no start keyword in Python. There is no stop keyword in Python. And that's what I mean. This is just loosey-goosey. It's just English. A C++ programmer starts their program in a completely different way than Python does. In Python, you just start typing, right? You don't have anything indented. You just start typing. In some other languages, you have to add some includes up at the top, and then you have to define a main function. And we don't have to do all that. That's why we're learning Python, because it's a little bit easier to dip into. So that's pseudocode. Input my number, set that, output my answer. Later on, we would want to draw a flowchart from that. How about we actually get to an example? Here we go, right? Start, input, output. We know by now that those go in the tilteds. Math, all the math goes in a block. Please put every math statement in its own block. If we're calculating miles per gallon and doing that, requires like 4 or 5 different math statements. Don't just put them all in one block. They need to go, in a series of blocks. If you wanted to put them all in one block, you could take those lines of code, put them in a function, and then call that function from there. But we're not there yet, not in this review. So we've seen basically almost all of the kinds of shapes that we need to do flow charting. There's one that this one doesn't demonstrate though, and it's the one that makes the code more complicated because it suddenly veers off, into another column and stuff like that. What is that? Yeah, the diamond, the if statement or the while statement goes in diamonds. It's called a decision or a selection. All right, this is how not to do it. This is supposed to repeat over and over and over. Well, that's spaghetti code. It's got, a jump or a go-to statement or like that. And diamonds are the way to implement loops. It's a control structure that dictates how we do things. Part of it. So, making a decision, you test a value, right? X less than 3, yeah, then we're going to do something. Y is equal to 0, well, that's going to produce an error message. So we're going to have if y equals 0. And a signal value is a value that ends your input and stops the program, right? Enter X or 0 to exit, right? That's a signal value. And let's tack that on as part of our notes. Signal value is a special input value that stops the program or the data entry, right? Example, enter X or 0 to exit, right? Enter test score or -1 to quit. It had better be a non-valid piece of data. If your teacher is a jerk enough to actually give you -1s on your exams, then that would not be a good signal value because they may need to actually type that. Now, we've played with a little bit using actually a different kind, right? Enter a number or Q to quit. That's way more awesome, right? Because you can't get a test score of a Q. And the logic for handling that's a little bit different. It doesn't matter what the signal value is logically, as long as it's something that's not valid data and the program can be written to test. While X not equal to 0, something like that, right? While choice not equals, Q. So the text editor is what we type into. Idle is our text editor. It's also, to some degree, an integrated development environment. That's where the I and the D from idle came from. Integrated development environment means you enter your text and you run the program all right there. Back in the olden days, they didn't have IDEs. You typed all your code into a command prompt, and then you ran the program by typing another command, and then you edited it again by typing another command, and stuff like that, right? It's much nicer to have it all in one program. So you're using Xcode on the Mac, or you're using idle, or something like that. We know what a command line is. The command line is just when you get something that you can type commands into. On Windows, it's called the CMD prompt. On the Mac, it's called the terminal. On Linux, I think it's also called the terminal or maybe the shell. In idle, it's the shell, right? We can type in commands right there. That's a command line. And then what do users like to see more than a command line? They like graphical user programs with buttons, right? Windows, stuff like that. And that was a big revolutionary change when they were introduced in the 70s. And then the Macintosh kind of brought them to the attention of the masses. And then Windows, came out, and was bought by a zillion people because they were cheaper than the Macs. And, then it's kind of been an arms race ever since. Who can make the best graphical user interface, so when it's easy to use and stuff like that. And believe it or not, even through the 80s, the real macho guys sneered at graphical user interfaces. That's just for babies. Point and click with a mouse. What kind of, but nowadays, absolutely everyone uses graphical user interfaces because they're very powerful, right? You would not want a command prompt to dial on your phone, right? Type in dial space, right? It's a stupid idea. Graphical user interfaces, everywhere. some of this stuff, a lot of this stuff would be from your test. I would just flat out take the chapter 1, 2, and 3 tests again. That's what I would do, right? Even if you got the wrong answers, it's not going to hurt you because, you know, it records your highest score. You know, just look at it. Try to get it right, but, you know, don't kill yourself trying to get it right. But, you know, make sure that you can answer every question in it because a lot of the test questions are driven from that. Chapter 2. Elements of high-quality programs. Declaring variables and constants. We know how to declare variables and constants. X is equal to 0. That's declaring a variable. A constant, you make an uppercase name. Now, since this is Word or PowerPoint or whatever, it made it uppercase for me anyways, right? Declaring a variable. In our language, we do it by giving it a value. That's how we declare a variable in our language. In some languages, you also have to give it a type. You have to say int x equals 3. This is also known as assigning a value, which means that the equal sign is called the assignment operator. That's different from double equals, which is a comparison, right? If x equals 3. What if it's a constant? Constant is a variable with a good name, right? Not just x, right? But, you know, tax underscore rate equals 0.07. Something like that. Constant. Give them uppercase names. Do you have to? Is that a law? No, it's just an agreement that, you know, a million other programmers follow, and so you may as well too. Some languages let you define a constant and then you're not allowed to change it later in the program. If I tried to reassign something else to it, then the program would give me a syntax error. Python's not like that. So we just have a gentleman's agreement that if we see a variable that's in all uppercase, we're going to treat it like it's a constant, and in your main code or function, you're not going to give it a new value. So this is a value. A constant is a value that does not change during the execution of the program. Right. Speed of light is a universal constant. Nothing is supposed to change it according to Einstein and other, you know, theoretical physicists. And so far, everything that people have tested seems to indicate that that's the case. Nothing is supposed to be able to exceed the speed of light. Other constants, you know, chemistry and physics have all sorts of constants. You know, maximum number of students in my program, max underscore students. Maybe my program only supports 100 students. Max underscore students equals 100, right? Things like that. Data types. Data types are how the data is represented in the computer. What kind of data can be stored? We've talked about several different kinds, and I'm just going to list some, and I want you to tell me what type they are. We've talked about these in the past. Now, one of these is a string. Which one is a string?
True or false?
Good guess. Not correct. Pardon? That one, the one in quotes. That's a string.
You can barely see it from here.
You can't see my writing?
No, it's going off the...
Oh, for Pete's sake. I don't know who Pete is, but for Pete's sake. All right. There we go. So, yeah, that's an integer. No, it's not. It's a string. You can't do math on a string. And a string is what you get from input. That's why we always convert it to a float, or an int if it has to be a whole number. So what kind is that? It's a number with no decimal point. That makes it a... Is it a float? Floats have decimal points. I was really hoping someone would answer that. Maybe I didn't give y'all enough time. This is an integer. a whole number. This is a float, which is a number with a decimal point. And lastly, we haven't talked about this a lot, but if it's a true-false, that's called a Boolean. There's a branch of math called Boolean math, Boolean algebra, which is a mathematical language in which there's only two possible values rather than a zillion possible values, you know, in normal math. Now, please be able to name these 4 data types. And we have played with one more data type, turtle. Turtle is a data type. Now, it's not built into the language, right? You have to import a library to get it to work. But it is a data type, right? You make a new turtle, and then you start giving it commands. It's a data type. Hopefully, by the end of this class, we will know how to make our own custom data types. So all programming languages support these data types, numeric and string. Seems a little bit overly broad, but all languages support numeric data, which are, in our language, float and int, and strings. Strings are what you type in from the keyboard. Books, right? Text. If you have some program like Siri or Hey Google, you know, you ask it a question and it's printing text on the screen. Those are strings. Two types of constants. These are known as unnamed constants because they don't have names. Right? Up here when I said x is equal to 3, or tax rate is equal to 0.07, there are numeric constants, which a lot of people call literals. That's just the number, 10.0. And then there are string constants, which are known as string literals. They're literally typed in the program. The user didn't type 10 in. I did. The user didn't type in input x. I typed it in, right? So if we do this, x is equal to 10, y is equal to input, parentheses like that, then 10 is a numeric constant. And y, oh, I forgot to put a string in there. What is y, question mark. Then 10 is a numeric constant, and what is y is a string constant. They're things that are just entered into the program by the programmer, not by the user. Right? They tell the user what to do. They're supposed to enter y, or we're going to do some math on x, so we give that a value. Some people call numeric literals magic numbers. Why is it set to 10? Well, I don't know. It's magic. Right. And usually if it's a magic number, it's not a bad idea to consider whether you should make it a named constant. Right. So numeric constants, sometimes called magic number, may be defined as named constants. Something with an uppercase, right? Max underscore value equals 10. Now it's got a name, so anywhere we want to use it later, we'll call it max value. Working with variables. Variables have data type, they have a name, and they have an initial value. So the three main components of a variable. A type, which we've talked about, int, float, string, whatever. They have a name, and they have a value. In this case, what type is max value? It's a whole number, so just set it paragraph or two up. What are whole numbers called in this language, or in every language? They're called integers, right. So the type of x is integer. In this case, what is the name of that variable? We gave it a name. What name is it? It's bigger than life. It's up at the top of the screen. Max underscore value. And then what is its value? What did we, yep, we stored a 10 in it, right? So all of our variables have three things. Now a complex variable like a turtle, it's got a whole bunch of things stored in it, right? It's got an x position and a y position and an angle that it's drawing and a color and a speed and all that. But pretty much our programs have all focused on, you know, simple pieces of data. Numbers and strings. So it'd been pretty easy if we wanted to describe the type and the name and the value of every variable in our program. Some textbooks would say that there's a fourth thing, that a variable has a memory address. Our language doesn't let you get to the memory address. Most languages don't. So I see why they left it out. And I know I'm going a little bit fast, but this is a review. So when you're using variables in some languages, you have to declare them up at the top. We don't have to. So declaring variables, we don't have to. You can make a block of declarations at the top of your program. You know, x equals 0, right? Speed equals 0. Stuff you're going to use later. Name is equal to 0. Then you will fill in these values later. So the textbook shows making a declaration block in your flowchart. Put a block, put some declarations. You can put all the declarations in a single block. Unlike when I said don't put multiple math statements, your declarations, the stuff at the top of the flowchart, they can all go. So a declaration defines the variables, gives it a type, and gives it a starting value. Declarations give a type, a name, and an initial value. Some people say that's an initializing statement. We've initialized x to 0. We have initialized name to be an empty string. Might come back to that, but probably not. The name, the book calls them identifiers. So when I say a variable has three things, name is called an identifier. It's not the only thing with an identifier. Function names are also identifiers. So if the book asked you to put the three things that a variable has, it would say type, name, and value. If you feel like putting a slash identifier here to make that easy to remember, that's okay. If you feel like going back and editing it, identifier, where it says variables have three things, feel free to modify that. Identifiers have to follow some rules. They should be a meaningful name. Single letter variable names are for the birds. The only reason I'm using them is because they're easy to type and time is of the essence. Should be meaningful names. They can be letters, digits, and underscores in our language. Some languages also allow dollar signs. No spaces in a variable name. You can't say first space name equals Joe. You have to do first underscore. And lastly, cannot start with a digit, right? So out of these three, tax rate underscore 2018, that's a good variable name. Tax rate 2018, that's bad because it's got a space in it. 2018 tax rate is bad because it begins with a digit. There are different ways you can name variables. The book absurdly calls this snake case. You put underscores in it. It's called snake case. Okay. The most commonly used way nowadays, kind of the new style that kind of kicked off in the 90s, is when you use uppercase letters in the middle of it. So that's good, right? They call it camel case because it's got a hump in the middle. And each additional word we needed, like tax underscore rate, local, right? We can make tax, capital R, rate, capital L, local, or local tax rate, right? We would just capitalize every letter, every word in it, except for the first one. I'm just going to put a comment. This is called camel case. Didn't make it up, sorry. This is called snake case. Didn't make that one up either. Until I saw this book, I had never heard that. But okay, I guess they needed a fancy name for it. One of the things I'm going to want you to be able to do is if I give you a flow chart, I know this is not going to be visible, and as an input, we need to be able to write code for an input statement. Now we see two ways of doing that. But if it's supposed to say enter age and then allow them to type in input, we pretty much have to do three things. We got to display the message known as prompt the user. So we're going to need a print, enter age. And then the next thing we're going to do is actually get the input. And in this language, the syntax is age equals input, parentheses in parentheses. And then the last thing we're going to do is we're going to convert it into a number, either with the int function or the float function. So let's say that. Getting input. We will display a message known as prompt. We're going to prompt the user. Yo, I want an age. We're going to have an input. And then if it's a number, we're going to convert it. If it's a number, if it's supposed to be a number, convert it. So every time we have a block in a code, you know, an input X kind of statement or input age in our flow chart, something like that, right? We need to turn that into some real code. We're going to have to do those three things. Alrighty, what word am I going to use? If it was pseudocode, I could use the word output. But we actually want to write Python, and so we're not going to use the word output. What word will we use? How do we display data? Come on, guys. Print. Yep. Print input age or enter age, something like that. And now we're going to get the age value. So we need an input statement. What's the syntax for input? Variable equals input parentheses in parentheses. This is like a test question or something. Age is equal to input parentheses in parentheses. Doesn't need the space. Doesn't matter if you put spaces there. It's all good. In my question, as possible, I would say remove all unnecessary spaces from your answer. It's not that I'm going to count you off. If you put a space in it, it just means that the auto grader is going to count it wrong. But then when I go back and double check like I do on every exam, it will fix it. And now I need to convert it to a number. A float's good enough for our age. What if the user wanted to say they were 17.5 years old? Age equals float, parentheses age. Like that. That's getting input. Now we need to make a decision with it, an if statement. There are two kinds of ifs. There are single alternative and dual alternative. We're going to give an example of a single alternative first. A single alternative is a something or nothing, right? Alternative. So if age is less than 18, colon, print, while you're young, in quote, in parentheses. That's a single alternative. It doesn't have an else. If we were going to draw it on a flow chart, it would have one branch going to a new column, like with a print statement, but the other line would just drop straight down, and then it hook back up, you know, with a circle underneath. A dual alternative has two different things, so it's got an else. One thing or the other. If age is greater than, I don't know how young kids go to school anymore, 5, colon, if age is greater than 5, we're going to tell them go to grade school, print elementary, and then I'm sure these values differ everywhere. When I went to school, then if, you know, junior high started at 7th grade, and I'm going to pretend that 13 is the cutoff age for junior high. Don't know. So else, colon, print, I don't know what we're going to print. Non-elementary, end quote, right? Something like that. And in dual alternatives, you can stack a lot of alternatives by using elif. You can stack alternatives with elif, or the book would call it an else if. If temperature less than 0, because it's Celsius, print cold, end quote, parentheses. Elif temperature is less than 100, colon, print warm, in parentheses, end quote, in parentheses, and then the final dangling else colon, print hot, right? It's no longer a dual alternative, but it's really a series of dual alternatives, right? Because if this is true, great. The alternative is to do all this other stuff. And then from the alternative, we're making another if case. If that was true, we're going to print warm, else we're going to print hot. So they are both forms of dual alternatives. We could rewrite this without an elif. Not gonna. Time is of the essence. Whatever that means. If the exam asks you what Pascal casing is, find a PowerPoint, Control F, look for the word Pascal. Oh, not in that one. Open another PowerPoint. I'm not going to ask you that, but all right. Assigning a value. In pseudocode, you use the word set to assign a value. In Python, you don't. You just use the equal sign. So, the equal sign, can I type? Oh, come on. Caps lock, okay. The equal symbol is the assignment operator. So A equals 3 is called assigning a value. Does it look like a declaration? Yeah, because in this language, assigning a value and declaring a variable, a value are the exact same thing. In other languages, that's not the case. What else? What other kinds of symbols are there other than equal sign? We've used a lot of symbols in the course of our programming. Other operators. Now, a symbol is something that's not a letter or a number, right? So what else have we used? And let's not count parentheses as an operator, because it's just part of the syntax. So what have we done? We type in a number, and then what do we often do with it?
Multiply.
Yeah, math operators. Math. Star, star. And then multiply and divide. And addition and subtraction. That happens to be the order of precedence as well. Except if we go by quote PEMDAS, then the parentheses are the first thing. Along with star and slash, we've seen two other ones. Slash slash, and what was the last weirdo one? I think I almost heard it. Be brave, speak up. Multiplication, division, floor division, and what's our word for remainder? What's our symbol for remainder? Come on, guys. If I wanted to get the remainder of 3 going into 10, what symbol would I have used? Yeah, the percent sign. So we know what star star means, right? What does that mean?
Multiply to the second power.
Right, right. Or not just the second power, but it's the power of, also known as exponent. We absolutely know what a star is. I'm not going to mention that. We absolutely know what a divide is. That's floor division. It divides and rounds down. So, x equals 5, floor division 3. What does that equal? Divide and round down. How many 3 times does 3 go into 5? 1 time. How about modulus? X equals 5 modulus 3. When 3 went into 5 1 time, what was our remainder? Right? 2? That making sense, guys? I was really sad that no one blurted out modulus when I asked. That's all right. You'll know for Thursday. What is x equals 6 modulus 3? 3 goes into 6 how many times? 2 with a remainder of 0, right? The reason I'm calling these out are these are the ones that we didn't use in our arithmetic up until this point, right? I don't recall in high school ever seeing floor division. And if we talked about modulus, we just called it the remainder. We didn't have a special symbol for it, if I recall correctly, unless you took a programming course. So, these are the highest priority. Let's go ahead and write them down. PEMDAS, parentheses, exponents, star and slash, and also slash slash and modulus are all considered forms of multiplication and division. Now, if I ask you to list things in their order of precedence, I'm probably not going to throw modulus or floor division, right? Just because our little mnemonic, please excuse my dear Aunt Sally, doesn't include them. And an addition and a subtraction. So if we have this expression, x equals 5 plus 2 star star 2 times 4. Now I'm going to put some spaces in here to make it easier to parse. Parse is a fancy word. How about that? Okay. What is going to get done first? Now, the mere fact that I've clustered some of them together, make it easy to spot what's going to happen first. But if I didn't have any spaces, the answer would still be the same. What's the first operation? Well, what has the highest priority, the highest precedence? Exponent. I don't know why I put a star there. Right. So, if we were doing this in our head, we would have to do the exponent first. And what's 2 to the power of 2? 2 squared is 4. All right, that's a 4 now. Then what do? Do we do addition or multiplication next? Multiplication. So 4 times 4 is 16. And then finally we can do the addition. 16 plus 5 is 21 if I did that in my head correctly. I'll just put out here as a comment that that's equal to 16. Be able to do that. If I give you a couple of questions like that, these are following rules that you'd already learned in the past. Initializing a value is giving it a starting value. It's the first time you assign something, you're initializing it. Initialize is giving a starting value. In our language, initializing and declaring are the same thing. That's not true of every language. As soon as you give it a starting value, that's called initializing. We know what a named constant is. Tax underscore rate equals 0.07. Rules of precedence. We've talked about those. The integer data type, whole numbers. Modules. A module is a block, a named block of code. That's my definition for it. Also known as a function in our particular language, is a named block of code. And the book will give different definitions. If I ask you to give me a definition and you take it out of the PowerPoint or something, that's fine. But it's a named block of code, right? These are defined with the def keyword. So, for example, I'm going to write a module called double. And what does it do? It returns the value of the parameter. So def double parentheses x in parentheses colon return 2 times x. So name of the module is double. The parameter name, parameter variable, is x. The act of creating modules can be called functional decomposition. It's just breaking up a large program into modules. It provides abstraction. The fact that we have a turtle module with functions in it means that I don't have to actually figure out how to put pixels on the screen myself. So, reasons to use modules. You can divide the tasks among various people. You can make sure that the code is reliable. All you have to do is test that module. Once you've tested it, you're pretty sure it works, and you can reuse it. So, reasons for modules. Divide into teams. You make them reliable so that you can reuse them. When you define a module with a flowchart, whoopsie, come back. You just put a circle up at the top. No, you don't. You put a circle at the top, but you put the function name rather than start. like that. And we've done that, right? Here's a module called display address. So we put that in this top circle. And do you remember when I did it, I colorized the calls, right? I had pink and pink there to let you know where it was going. You don't have to do that. If I ask you to draw a flow chart, it's going to be a real easy flow chart. Like a single if statement and no loops. A hierarchy chart. I'm not going to ask a single thing about a hierarchy chart. It just shows you what modules call what modules. This is a simple program. It has 3 modules. Here's a more complex program where modules call modules. That's totally acceptable. Comments. Programs should have comments in them to describe what they are doing. Your variable name should be chosen carefully. You should try to write clear statements. You should echo your input, meaning that when you're displaying your results, we should have been displaying, you know, temperature in C as well as temperature in F so that they know what they typed in was correct. Just like putting somebody's address and name on an invoice, knowing that they got it. Some of these statements we've been doing from day one, like using comments, so I'm skipping those. We're about out of time, but I still want to hit the Chapter 3 PowerPoint. So we're going to do that. Let's get to Chapter 3. Next 4 minutes. How about that? We'll see. I never can remember if class is 70 minutes long or 75. And Chapter 3. Understanding structure. We learned about spaghetti code. Unstructured programs do not follow structured logic. What is structured logic? There's 3 structures. There's sequence, there's selection, and then there's loops. Sequence are the stuff in a straight line. Selection are if statements. And then loop is repeated code. This is worth writing back in our notes. Programming structures. Sequential, just a series of lines. Indentation level doesn't change. Series of statements, indentation doesn't change. Then there are selection, also known as decisions, and our selection has been the if keyword, or if then, or if else, I mean. Single selection and dual selection. We've already talked about that, so I'm not going to belabor that. And then there's repetition. Repetition, which is looping, which means repeat code while the statement, while a condition is true. If I ask you to list the 3 programming structures, I'm expecting you to be able to spit out sequential and selection and repetition. And good thing it's in the PowerPoint, right? Control F, find the term structure, and boom, you will get to a page based on that. But hopefully you know a lot of this so you don't have to spend too much time looking. Right, we recognize the selection. If. How do we know it's not a while? What's different about an if and a while? An if joins back up at the bottom. We've been putting a circle there where they join. What does a while do? I'm pretty sure we flowcharted a while, have we not?
Yes.
The line goes off that way, does some stuff, and then hooks back up, right? It doesn't have a no side. The no side just goes straight down. It has a block and an arrow coming back up to it. That's a while. That's a loop. Yep, a loop. We've talked about single and alternatives and dual alternatives. Each repeating of a loop is called a repetition or an iteration. Each repeat of a loop is called repetition, makes sense, or iteration. There's a loop structure, except I always draw the line going back to the diamond. They draw it going above it. Doesn't matter. Same thing. So while you continue to be hungry, take another bite of food. While x is less than 0, print x, add 1 to x. And everything you do in programming can be done by combining those structures. You can stack the structures, right? You can put ifs and whiles and you know, sequential all in a row, or you can nest structures. You have an if followed by a while, you know, stuff like that. So let's put those as ways of combining structures. And this is going to be the last thing we put. Right? Stacking them. Make sure that that's what they call them. Yep. And nesting them. Not besting them. And you know what a nest is. It's when one structure is inside another one. It's when you tab over. Making a new column. Alrighty. We can make a Dropbox for you these notes so that you have them available to you. Any questions? It doesn't matter if this code actually worked or not. You saw how little code I actually put in it. So this is JKL. Exam review. Chapters 1, 2, and 3. Do use that How to Think Like a Computer Scientist. Just open it up and read it. Not necessarily for the exam. Yeah, you can go to it if you want, right? For the exam, you'd be better served by reviewing your C-Engage exams. And don't panic, guys. Open notes, open book, open waving your hand and asking the professor to explain. If I explain it to you, I'll probably get up here and explain it to everybody, so it's, you know, a cool thing to do. And if you totally run out of time before the exam is done, I'll let you close your exam and then go and complete it at the library, right? So if you run out of time, it's not another panic situation. Sound good? I'm hoping lots of people make A's. I like for people to get a really good grade on the first block of the, you know, of the course, so that they feel, you know, more confident getting into the second one. And even though the second one's going to be more difficult, you've already got a really good foundation, grade-wise and knowledge-wise. Any questions?